2 of AAAI 26. Thanks for a great first day, and we're looking forward to another fabulous day with a great set of plenary talks, technical sessions, and many different activities across the conference. We're going to start off with our first plenary talk, and for that, I would like to bring to the stage Joydeep Biswas, who's going to introduce our first speaker of the day.
Thanks, Chad. Good morning, everyone. I'm thrilled to introduce our invited speaker, Professor Daniel Whiteson. Daniel is a particle physicist and a professor of physics at the University of California, Irvine. And his work sits at the intersection of machine learning, fundamental physics, and it essentially is about data-driven scientific discovery. He's essentially looking into using AI techniques to learn about the fundamental nature of energy and matter, including data from CERN's Large Hadron Collider. So beyond his research, Daniel is also an amazing science communicator. He co-hosts the current podcast, Daniel and Kelly's Extraordinary Universe, and a previous podcast, Daniel and Jorge Explain the Universe. He's also the author of several popular physics books, including my favorite physics book, which is called We Have No Idea. And so please join me in giving a warm welcome to Daniel Whiteson.
Wonderful. Good morning, everybody. Very excited to be here. Thanks very much for turning up for this session at 8 in the morning Singapore time, though I know it's, of course, 6 p.m. or whatever in California, so we're all adjusted. I'm here to talk to you today about machine learning and fundamental physics. And the technical staff have assured me that my slides will appear momentarily. So until then, I just have to ad-lib. Are we preparing the slides? Here we are, yay, all right. So indeed, I'm talking today about machine learning and fundamental physics. I'll also tell you a little bit about my journey in science communication, both the joys and the challenges that I faced in being an academic, also talking to the public. But first, I want to talk about fundamental physics. The thing that got me excited about fundamental physics when I was a young kid choosing my direction in science was the fact that it asks big questions. And I don't mean like, which mattress is going to get you through the night. I mean the kind of questions which, if you knew the answer, would change the way you felt about life, would change how you lived your life, the choices that you made on a day-to-day basis. All right, so what's an example of a really big question? Well, if you ask random people, what are the biggest questions, they might say things like, why are we here? Or what happens after we die? After all, if you knew for a fact what happened after we die, it might change the way you live your life, right? The thing with these questions is that they're wonderful questions, but they're philosophy questions. They're questions like, what is it like to be a bat? This is not a joke, by the way. This is the title of the most widely cited philosophy paper of all time. What is it like to be a bat? And the thing about these questions is that they're wonderful to think about, they're wonderful to talk about, they do matter, but sometimes I wonder if all you can really do is just sort of like talk about them late at night in your dorm room. We don't really ever make progress on these big questions, right? And so the thing that excited me about physics is that there are other big questions in physics, like what is everything made out of? Or how did everything begin? And these are science questions. These are questions that have answers that we can actually unravel, things we can learn. Someday, somebody will know the answer to these questions, and we won't have to speculate about them at 2 a.m. in the dorm room. All right, so I can't talk about all of these questions, but the one that I dedicated my life to is this one. What is the universe made out of? And this is a very basic question, right? I want to know what I'm made out of, what you're made out of. How does this whole thing work? How does everything put together to explain this incredible, glorious universe that we find ourselves in? I think this is also, in addition to being a basic question, it's an ancient question. It's the kind of thing that people have been asking themselves since people have been asking questions, right? You don't need to have more than just 2 rocks and bang them together to try to understand, like, what happens here? Do I get smaller rocks? Do they turn into something else? What's the smallest possible rock, right? These are basic questions you can ask yourself if you're a curious person in the universe. And so I think people have been asking these things for a long time. So imagine you're the first person to ever think of this question. What is the universe made out of? How do you attack such a big question? How do you search for an answer for this question? Well, you might start by doing the simplest thing, which is just make a list of all the things that you see in the universe, to begin with a catalog, right? So if you're caveman, cavewoman scientist, your list might say this, right? I'm in the universe, you're in the universe, here's a rock, there's a rock. And as you begin developing your list, you realize, wow, there's lots of different kinds of rocks in the universe. And the list grows very, very long until you discover like every possible kind of rock that's out there in the universe, right? And this highlights the problem with this strategy is that we're not looking for a catalog of everything that's in the universe. The answer to the question, what is the universe made out of, is not a list of everything that's in the universe, right? That wouldn't be satisfying. If you could speak to the oracle or to God or to advanced aliens or the AI, and you asked it, what's the universe made out of? And it just told you everything that was in it, you wouldn't feel like that aha moment, the thing we're looking for. Instead, the goal of particle physics is to explain everything that's in the universe by reducing it, by saying, oh, it's actually built out of a small set of objects, right? Things that we can put together to make all of this complexity. And it's kind of amazing that we can explain me and you and rocks and the rock and everything you had for breakfast today and through years and years and years and anything anybody has ever eaten or touched. All of these things are built from a few basic building blocks. That's incredible, right? That the universe works that way. That complexity comes from the arrangement of smaller things. Now, we have this 100 or so elements of the periodic table. And of course, that's not the end, right? Because what do you do with these 100 elements? You don't just list them. A list is not an answer. You organize them. You categorize them. You look for patterns. And of course, it's a periodic table. There are patterns. And now we know that all the patterns in the periodic table also emerge from the arrangement of smaller things, right? So the complexity, on one hand, the periodic table is very simple. On the other hand, it's very complex. And that complexity arises from the rearrangement of just 3 particles. Up quarks and down quarks put together give you protons or neutrons, add electrons, and you can make anything anybody has ever touched or eaten or thrown at their brother. And that's kind of incredible. That tells you already something very deep about the universe. It tells you that what makes you, you, is the arrangement of the particles, not the particles themselves. Like the only difference between a kilogram of lava and a kilogram of kittens is how the particles are put together. It's the same ingredients. If you ask a particle physicist to write a cookbook, every recipe has exactly the same ingredients in basically the same proportions. So already, physics has told us something fundamental about the universe, that it's arrangement that's key and not the substrate. Okay, but this isn't, of course, the answer. There are more particles out there. And as we smash things together in our colliders, we reveal that there are partners to the up quark. There are 2 other versions of it, the charm and the top. And they're partners to the down quark, the strange and the bottom. The electron has 2 partners also. And now we have a new table. This table is the cutting edge of human knowledge. This is the periodic table of the fundamental particles. And we don't know what underlies this, but we see patterns. We see lots of fascinating structure here, which suggests, if the pattern holds, that this emerges, again, from the arrangement of something smaller, yet more fundamental. But we don't know. And so here we are at the forefront of human knowledge, not knowing the answers to very basic questions about all of these bits. Like, why do we have these other particles? We have the up quark, cool. You can use that to make iron and stars and all sorts of stuff. Why do you need the charm quark or the top quark? Why do we have 3 neutrinos? Why are there more particles out there? Why are some of these really, really massive and some of these really, really light? Why do they have these weird charges, plus 2/3? Who ever heard of that? So there's a lot we still don't understand about the fundamental particles. And that's not even the biggest unanswered question. All of these things, everything we've understood, everything we've studied for years and years and years, only represents a tiny slice of the universe. 5% of the energy density of the universe is made up of atoms, stuff like me and you and birthday cakes. The rest of it is basically unknown. There's a huge chunk called dark matter, about 25-ish%. Dark matter is something we know something about. We've seen its effects out there in the universe. Galaxies are spinning, and if you put ping pong balls on a merry-go-round, for example, you know that if you spin it, the ping pong balls fly out. So if galaxies are made of stars and they're spinning, why don't the stars fly out into interstellar space, intergalactic space? Well, the answer is gravity. Gravity is holding the galaxy together. But you can do this cool thing where you measure the velocity of the stars and you compare it to how much gravity there is from those stars, and it doesn't add up. The stars are going way too fast. There's not nearly enough gravity to explain why the galaxies aren't throwing their stars out into space. So we invented this concept called dark matter to explain how the galaxies are coming together. And there's a lot more dark matter than there is normal matter. And so we're just at the beginning of this exploration of the fundamental nature of matter. You know, we've been studying atoms and elements and quarks for hundreds or thousands of years, depending how much credit you give to the Greeks. But now we know that it's like we've been studying the tail of the elephant. And only now do we realize that there's more to the story. And our temptation when we do this is to extrapolate from what we know to what we don't know, to say, well, probably dark matter looks like normal matter, similar, right? It must be. But, you know, does the rest of the elephant look like a tail? The rest of the elephant is not built out of tails. It's something new and fundamentally different. And that's where we are in fundamental physics. We know we are on the verge of discovering things which will change completely our understanding of the nature of the universe. And we haven't even talked about the biggest part of that pie, right? 5% is atomic matter. 25% is dark matter. We're pretty sure it's matter. We don't know what it's made out of or how it works. The rest of it, 70% of the energy budget of the universe, something we call dark energy. The relationship between dark matter and dark energy is literally just the word dark, which physicists use for like, we don't really know what this thing is, okay? They're very different concepts. Dark energy is responsible for accelerating the expansion of the universe, but there's no well-understood mechanism or not even a complete coherent theory of what dark energy is and how it might work. So there's a lot left to figure out about the universe. How do we figure it out? Well, the strategy is to look for the mysteries and then pull on those threads, right? Tug on them. You never know which little weird experiment or which cross-check you do is going to be the thing that unravels completely our understanding of the universe. If you look back in history, small little experiments, the photoelectric effect, the ultraviolet catastrophe, the Michelson-Morley experiment, these little experiments change the course of our understanding of the universe. So I don't work at a little experiment. I work at one of the biggest experiments in the world, the Large Hadron Collider outside Geneva at CERN, the European and basically the international headquarters of particle physics, where we have proton-proton collisions at 13 tera electron volts. That's 13,000 times the energy stored in a single proton. So very, very high energy collisions, the highest controlled energy collisions in the world, though the universe is sending us particles at much higher energy all of the time. But humans, this is the best that we've accomplished so far. The most exciting thing about the Large Hadron Collider is not smashing particles together and seeing little explosions. It's that we don't know in advance what's going to come out of these collisions. And we don't have to know in advance, because when you smash these two particles together, their energy, they annihilate with each other, and you get a little ball of energy, which can then turn into something else. So particle collisions are not like chemistry, where you have the inputs and the outputs, and the outputs are basically just like a rearrangement of the inputs, so you can follow every oxygen molecule from the initial state to the final state. No, the initial state is annihilated. It disappears. And then the universe uses that energy budget to make something new, which means something awesome and incredible. It means you don't have to know that something is there in order to discover it. If you smash these particles together often enough, the universe will make everything that it can make, because these collisions are quantum mechanical. So two collisions with exactly the same conditions can create two different outcomes. It's a random process. We are sampling from the density of the universe. And that's cool. It means that you can smash these particles together, and sometimes you get things you know, like electrons, or you get other things you've seen before, like muons. But sometimes you smash these particles together and something new comes out, something you've never seen before. Again, you didn't even have to know that it might exist in order to discover it. That's the joy. So let's get a little bit more concrete. We make these particles. How do you know when you've seen a new particle, right? What does it look like? Well, you're used to like zooming in with a microscope to see these things in a tiny way, but these things are much, much smaller than any wavelength of light you could use to probe them. So you can't image them in a conventional way. Here's a video showing us. Here we are zooming in from space. This is where CERN is, just outside Geneva. It's a wonderful location if you've never visited, nestled between the Alps and other mountains. There's fields of sunflowers. Here's the CERN campus, just outside Geneva. And this is the ATLAS experiment. This is where I work. And it's underground by 100 meters. There's an elevator with two buttons on it, 0 and -1. And this surrounds the collision point with layers and layers of detectors that tell us what came out of the collision. Here's a graduate student for scale, though you're not actually allowed to walk on the detector. And so this whole apparatus is just to image what happens when we smash these particles together. We can never see any of the products directly. Instead, what happens, so particles smash together and then they fly out sideways. We have some detectors that tell us the paths of particles, other ones that measure their energy, et cetera, et cetera. And so it's from this kind of image that we try to deduce what happened in this collision. Was it an electron? Was it a muon? Was it something new and strange? So that's very cool. We have these very cutting edge detectors, but what do we need machine learning to discover these particles? What is the role of machine learning? Well, it used to be that we didn't. So 100 years ago, when Paul Anderson discovered the positron, for example, he did so by finding one example. This image on the left is a single positron, and he can tell it's a positron because the way it curves in a magnetic field. One image, one particle, one Nobel Prize. That's the dream, right? But you know, the old guys have done all the good stuff, all the high rate stuff with no background where you can discover things like this, where a discovery is like finding a unicorn in the woods. Like maybe it's hard to find a unicorn, but once you bring it into town, everybody agrees it's a unicorn, right? These days, discoveries are much more indirect. So for example, the Higgs boson is not like that. We don't have a picture of the Higgs boson. Instead, what happens is you smash two particles together, two protons in this case, and if the two gluons inside those protons fuse together, they can make a Higgs momentarily for like 10 to the negative 23 seconds, and then it decays into something else, like two bottom quarks. And those bottom quarks we can see in our detectors, so we never see the Higgs directly. And you might think, great, if you see two bottom quarks, you found the Higgs, right? Wrong. Unfortunately, there's lots of ways to make bottom quarks. So in fact, bottom quarks is one of the most common things to make, and you can make them without the Higgs boson. You can make them with just a gluon in the middle. So you see two bottom quarks, how do you know it was the Higgs boson? You can't ever tell that an individual collision had a Higgs boson in it, which means that all of our discoveries these days are statistical. So this is what the Higgs boson discovery looked like. There's no single example I can show you of a Higgs boson. There's a little bump on a curve, and that bump suggests the Higgs is there, because if the bump wasn't there, there would be no Higgs. So these discoveries are statistical. Fortunately, statisticians are smart, and they've given us very powerful tools to make these discoveries. Specifically, we rely on hypothesis testing, which uses the Neyman-Pearson lemma, and it says, look, you want to know if you've discovered something, just calculate the likelihood ratio. Say, what's the probability of your data what's your probability of the data if the Higgs exists? What's your probability of the data if the Higgs doesn't exist? Take the ratio, you're done, right? Easy peasy. This is an amazing, huge leap forward in statistics. We still rely on it 100 years later. And it's amazing because, you know, there's lots of different ways you can analyze your data. What function you put your data into to analyze. And the likelihood ratio is the global optimum. If all of function space, this is the one you want to use to discover your particles. Fantastic, right? We're all set. This is well-established statistical theory. Yeah, that's cool if you can calculate the probability of seeing your data given the Higgs boson. or the probability of seeing your data given not the Higgs boson. You might think, well, Daniel, you guys designed this experiment, you built it, you run it, you're a particle physicist. Why can't you calculate the probability of seeing your data given the Higgs boson? That's why you designed the experiment in this way, right? Yeah, well, particle physics is messy. We can do some calculations, but we cannot calculate every step. I've given you a cartoon picture of what happens, but in reality, it's much more complicated. These particles interact, they're surrounded by other particles that interact, those particles make other particles. When they smash into detectors, they trigger a shower of particles, trillions and trillions and trillions of particles. There's no way we could write down analytically the probability of seeing some detector response given the Higgs boson. It's just impossible. So we wouldn't need machine learning if we could do that. If we could just express the likelihood of our data, we'd be done. I wouldn't be at this conference. Nobody in particle physics would be using AI, but we can't. But of course, we could do something. We can't calculate the probability of seeing our data given theory, but we can simulate it. We have this high fidelity simulation, which takes it step by step, propagating an example collision forward to give us one example. And we aren't the only ones who use simulations. When you try to predict, for example, the path of a hurricane, you calculate possible trajectories, and then of course you take out your Sharpie and you modify it if it doesn't agree with your politics. But at its core, what you're doing is you simulate a bunch of examples, and from that you infer a density. Right? You say, oh, I don't know, I can't calculate the probability of this hurricane hitting Alabama, but I can run 1 million simulations. I can tell you that it happens 3 out of 1,000 times, right? So if you have simulations, you can infer it. But the problem is that simulations give you data, but inferring that density in high dimensions is a challenge. In 1 dimension, maybe you need 1,000 examples. In 2 dimensions, you need 1,000 squared. In n dimensions, you need 1,000 to the n, right? All right, well, what's the dimensionality of our data? It's about 100 million, all right? So does anybody out there have enough computing power to generate 1,000 to the 100 million simulations? That's more than the number of particles in the observable universe, right? So that might feel like, okay, well, this whole thing is a waste of time. How do you even do this? So again, we wouldn't need machine learning if we could express the likelihood of seeing our data, or if we had infinite computing resources, or infinitely fast simulation, which is equivalent. So what do we actually do? We don't deal with the full data, right? What we do is we take the full data set, which at its initial level is like 10 to the 7, and then we sparsify it. We say, well, let's only focus on the parts of the detector that have any hits in them, where something happened. That's 10 to the 3. And then we string those things together. We say, oh, all of these traces are from one particle. We can call this one thing. We're down to like 10 to the 2. And then we look at the ones we're interested in, cut down by half, and then we boil it down into one number. So billions of dollars, all of this energy, massive complexity, 100 million samples, down to one number. And we do that because that's about all we can handle. If we're going to simulate the output of a collision, remember I showed you the Higgs boson graph, that was a single number per collision. That's the level at which we can calculate. So we wouldn't need machine learning if we could calculate what was going to happen in our detector, or if we had infinitely fast simulation, or if we could summarize all of the information perfectly in one number, we wouldn't need machine learning. But we can't do any of those things. When we do this summary, we always lose information. So we've been doing machine learning a long time in particle physics. Before the deep learning revolution in 2012, basically what we would do is say, look, our data analysis can only handle one feature, basically. So if you want to include multiple ones, you got to boil them together somehow. And so we used machine learning. This is a paper from 1997, right? Using machine learning to boil together a few different pieces of information from one collision into one number. And then the histograms are simulations of those two hypotheses. And you can see, look, we can reconstruct the density, and then you can compare to data, and you can see what the universe tells you. That's very cool. And for those of us who are old enough, we've been doing machine learning well before it was cool. Here's a paper I wrote in 2007, almost 20 years ago, with my brother, who's an actual AI researcher at Oxford. So this is the first paper that had 2 Whitesons on it, which was a fun milestone for me. But back in the day, we used machine learning, but we used shallow networks, right? We didn't know how to train anything deep, and there was this lore. There was this paper that said, All you need is a single hidden layer. With a single hidden layer, you can express any function. Now, there was an important caveat in that paper, which everybody forgot to mention when they were quoting it, which is, well, that hidden layer might have to be infinitely large in order to capture all the expressivity, right? And we use this paper, this lore all the time to convince ourselves that, look, one hidden layer was fine. We also knew that it wasn't fine. We knew that it wasn't enough. And in the language of searching the space of functions, if the likelihood ratio is the optimal point, these shallow networks were only really capturing a small set of that space. And we could search that space and we could find the shallow optimum, but it wasn't anywhere near that, the real optimum. And we knew this. We knew that neural networks were kind of dumb. You put your data into them and they wouldn't do very well. And you'd re-engineer the features and then they would do better. And you think, why do I need to do that? If the neural network can capture the information, I shouldn't have to do feature engineering before I give it the data, but I did have to, which tells you neural networks weren't smart enough. They were not searching the whole space of functions. And the functions we needed involved highly nonlinear convolutions, which these shallow networks couldn't do. All right, so 2012, deep learning. We have new tricks for training these things. We know that we can get much better expressivity by using deeper networks. Same number of nodes, just rearranged. In a deeper network, you get nonlinear effects from multiple convolutions, and now you can explore a bigger space of functions. Neural networks are very powerful. And so these kind of neural networks were actually used in the discovery of the Higgs boson as early as 2012. Very exciting. And now machine learning is everywhere in particle physics. We use it, of course, to classify our data, but we also use it for lots of other things. We use it to generate simulated data. The simulations I told you about that follow all those trillions and trillions of particles, that's the biggest fraction of CERN's computing budget, which is a very, very large budget, because those simulations are expensive and slow. So instead, we just train networks to generate examples, right? Feed it noise, it samples from a latent space, and then it maps from that to some realistic output. So now we can generate data in the blink of an eye, simulated data in the blink of an eye, rather than running CPU hours, thousands and thousands of hours. Really transformational application of Gen AI in machine learning. We also do more than just feed numbers into our networks. We use structured data. I'll talk to you a little bit more detail about this in a minute. And we don't require training networks to have perfect labels. We use things like weak supervision, where you have mixed samples with different proportions to extract information in more subtle ways. Finally, we're excited about optimizing basically everything, not just once you've built the experiment, analyzing the data in the most powerful way, but also optimizing the design of the experiment itself, right? Imagine configuration space for a new particle collider and detectors. What size is going to be the most optimal for making discovery? Well, if you can calculate that and you can differentiate it, then you can search that space for the optimum. So now AutoGrad tools are very, very useful for optimizing the design of future facilities. We've even applied machine learning to particle theory, right? Not just analyzing data from collisions, but also thinking about the high parametric spaces of particle theories. If you've heard of supersymmetry, it's this theory the universe that has hundreds of parameters, which means searching that space is impossibly hard. But of course, machine learning, excellent at searching high dimensional spaces. So there's a big effort there. But I'm hoping for something even greater. I'm hoping that machine learning will not just improve our ability to analyze our data, but that it might make new kinds of discoveries possible. Things that we once thought were totally impossible, we're hoping tools from machine learning will make those discoveries possible now. So remember the single event discoveries I told you about, the positron, right? One example, one Nobel Prize. We'd all love to return to those days. One of the challenges with the experiments we do now is at the very high rate. When you're looking for rare things, you need lots of collisions. And we have collisions every 25 nanoseconds. And so we used to look for tracks using these computers, right? Literally people looking at displays, using their brains to find paths through these detectors. That's too slow for the tsunami of data we have now. So we had to move to computerized, digitized tracking. So tracking is a challenging problem. Here's the statement of it. Particles leave traces in our layers of detector, right? But we have to come back and reconstruct those traces and say, oh, these traces together, these were a particle. So you have a detector in which you have thousands and thousands of particles leaving tens of thousands of traces. Your task is figure out which traces go to which particle. And combinatorics are huge here, right? Tens of thousands of particles. How many ways are there to assign all these traces? Zillions. It's impossible to do via brute force. And so what people have done is simplify the problem. They say, well, let's assume that the particle has to begin where the collision happened, because that's where most particles are created. Reasonable assumption, fine. Another assumption is that particles follow a certain trajectory. We can use electrodynamics to say if it has an electric charge and there's a magnetic field, we know it's going to move as a helix. Cool, that's reasonable. And these assumptions are fine, but they also limit our ability to discover things that violate those assumptions. We've recognized this in particle physics in the last 10 years when we've realized that there are ways that particles could be created not at the collision point. Maybe something big and heavy floats for a while and then explodes, leaving a shower of particles. We should be open-minded to these kinds of discoveries. And now people are working on these things. They're called long-lived particles or displaced particles. Great projects. But I'm interested in this other assumption that particles have to move as helices. This assumption is deeply woven into our current algorithms, which uses things like a Kalman filter. Essentially, you assume the form of your particle path, you get a few candidate hits, you fit your trajectory to that, and then you use that to propagate it forwards and search for the next hit. This is very powerful because if you have an idea of where your particle went, you don't have to search on the other side of the detector for potential hits. It narrows your search for other hits down dramatically. But it also means you're assuming the direction, the trajectory of your particle path. You're assuming it moved as a helix. What if it didn't? So I would like to be able to search for things that are not helices. There could be something dramatic waiting for us in our data that's not a helix that you could look at and say, oh, that's something new and cool. It doesn't move the way we expect. That's the kind of discovery we're all excited about. Currently, our algorithms cannot see that. It could be in our data right now. We could have processed those collisions and just discarded them because we didn't see anything, because we didn't know how to look for this kind of discovery. So how could we make this kind of discovery? Well, this is the kind of thing that I'm very excited to look for, because I didn't get into fundamental physics to make some small incremental discovery. My dream is to find something where when I take it to the theorist, they go, what? That's impossible. There's no way that could even exist, right? That's been ruled out already, because that's the kind of discovery that upends our understanding of the universe, that inspires a revolution in physics. So can machine learning help us solve this problem? Can it help us find particles with weird paths to them? So I think that it can, because there's this technique using graph neural networks to find these particles. It was actually invented for a completely different reason. In the upcoming runs of the collider, things are going to get very, very messy, very, very intense, and very busy. And they developed this graph neural network-based particle tracking algorithm to be able to handle these very dense environments. And it works really, really well. But I noticed that it does something crucial. It separates the assumption of track finding, which hits belong to my particle, and track fitting. What shape am I fitting it to? What parametric function am I imposing on this thing? It separates those, and nowhere does it assume a helical path. It just trains the network to find helices by giving it a bunch of examples. It's a very cool strategy. I won't go into great details, but essentially it learns a mapping from physical space of the hits to some latent space. And in that latent space, particle hits that are from the same track are near each other, and particle hits that are not on the same track are far apart. So it becomes easier to do tracking. Very cool strategy. And again, it does not ever implicitly assume a helical path. So can machine learning help us generalize tracking to find new weird non-helical particles? And so it's possible to have these other kinds of particles, right? They don't have to violate physics in order to exist. Particles move as a helix in magnetic fields because they have charge under electromagnetism, but there are other kinds of charge. What if you're charged under magnetism? A monopole, for example. That doesn't move as a helix. There are even other weird particles called quarks, which are theoretical particles, which are hypothesized to have a new weird kind of dark force between them. And when you create them, they oscillate in the detector, giving spectacular examples like this. This is an example. These are simulations, of course, but if you saw one of these things in your collision, you would buy your ticket to Stockholm that afternoon, right? This is Nobel Prize winning discovery on a single event. Very exciting. If only we could see them in our data, right? So we worked on a project to use this kind of machine learning based tracking and trained it instead of on standard model helices, trained it on these quirks. Could it find quirks? Here's an example of it finding quirks. Again, these are simulations. I'm not announcing the discovery of a new particle today, but we showed that it can. These machine learning based trackers can actually find new kinds of particles, things that don't move as a helix. It's very exciting. So we put out a paper last year, a lot of fun. But our actual goal is not to find quirks, right? Because you could always develop a single bespoke tracker to find quirks. Our goal is to find something new and weird, something unexpected, not something theorized by some clever guy in California. We wanted to find something we didn't anticipate. So we said, well, could we find anything that's any kind of smooth path at all, right? Anything that moves through space and has a trajectory which is continuous and whose derivatives are also continuous. Well, mathematically, you can describe this in Fourier space. You can just map this to Fourier space and use that to explore the space of possible particle paths. And as long as you impose that high frequency modes have very, very low amplitude, then you get smooth paths. It's something called a Schwartz function, which my grad student discovered I didn't know anything about. And so we were able to generate a bunch of weird tracks that don't come from any specific particle theory. They're just paths through space, simulate what they look like in our detector, and then train a machine learning-based tracker to find them. Here you can see it succeeding. The green circles are things that it found. It said, oh, here's a particle. And it's not perfect, it doesn't find the entire particle, but it finds enough to make a discovery. If I saw one of these things in a real collision, I would be calling up Swedish Air and buying a ticket. So to end up the scientific portion of my presentation today, machine learning-based tracking is very powerful. Machine learning has revolutionized physics. It touches everything we do in particle physics. And it's so powerful that it doesn't just optimize our discoveries, it makes new kinds of discoveries possible. As for example, the weird tracks that I showed you. All right, so I also want to tell you about my experience in science communication. First of all, you might ask, well, why do science communication? I seem like a busy guy, got plenty to do. Why spend my time also talking to the public about science? Well, I think our science is worth communicating, right? This is exciting stuff. We're unraveling the nature of the universe here. We're revealing its basic bits. We're discovering things that are going to go in history books, right? This is interesting. It's fascinating. It's important, not just to me, but to lots of people out there. And remember that science is not just our day job. It's something we do for society. It's paid for by people. It's done by people. And it's done on behalf of the public. And so I think it's important that we communicate what we've learned using largely government funding to the public who supports it. Their support is crucial. Plus, it's super cool stuff, and they want to hear about it. Not only that, I think it's vital to have an informed and educated public, not only so they can make good decisions when they're in the voting booth, but also they can make good policy if they happen to be elected.
We have forgotten because we keep hearing that 2014 has been the warmest year on record. I asked the chair, you know what this is? It's a snowball, and that's just from outside here.
Here's a man who thinks that the existence of a snowball disproves global warming, right? Clearly, there is more education to be done here. Clearly, we could be communicating our science more effectively. So I've written a few books for a popular audience. I have a couple of podcasts and a television show on PBS. And I'll tell you a little bit about my experience, including reasons why you might not want to do science communication. I've done it for a couple of decades now, and invariably, when I see colleagues from around the world, they ask me, oh, Daniel, I saw you put out a new book. Are you still doing any research? Are you still doing any research? Because the presumption is that you can't possibly do research and be at a high level and also talk to the public. For some reason, this is a persistent myth. All right, so how should we communicate to the public? Well, the typical way that this goes is you do some work, you write a paper, maybe your university puts out a press release, right? Maybe a reporter reads that, gets excited about it, talks to their editor, writes an article, it goes out there on the internet, your grandma reads it, right? But by the time it's gone through this whole cycle, sometimes nuance has been lost. And you get articles like this, right? Scientists just successfully teleported an object into space, man. Cool, like this is an amazing piece of work and it's really excellent, but what you think this means is not what it actually means, okay? And a lot has been lost. Even in my own field, like here's the coverage of the discovery of the Higgs boson in the New York Times, where they say that we have revealed the deepest layer of reality our species has ever probed. And like, I'm into philosophy and I don't even really know like what that means. What is he talking about here anyway? And the more you read like the science section in the New York Times, the more you see stuff like this. Here's a study that showed that the number of books in your house was the most important predictor of your child's academic success. All right, but like we're not saying, they're not gonna say, oh yeah. They say what you should do is go out and buy a bunch of books. Just fill your house with books. That's the best thing you can do for your kids, right? Because hey, these two things are correlated. And as we know, everything that's correlated is causally connected, right? Internet Explorer is the reason for the murder rate. Now, you guys are smart folks. You know the difference between correlation and causation, but not everybody else out there does. And sometimes it's really important to explain these things clearly. Here's a positive example of science being explained very clearly. And you know, it's a shame when you have to go to the Onion, but at least they got the story right, you know? They are bang on. I have no science complaints. The other frustration I have with science communication is sometimes it's told to you like this. Here's a cartoon from the New Yorker talking about the Large Hadron Collider. I saw this, I was so excited. Oh my God, my field in the New Yorker, right? Well, look at the last panel. If I concentrate ultra hard, will I ever be able to understand it? No. Just no. Don't even try. It's a waste of your time. It's not for you, right? This is for a bunch of nerds. And that's exactly the opposite message we should be sending, right? This is for everybody. This is accessible to everybody. Okay, so maybe journalists and cartoonists aren't the best way to communicate science. What about science communication by scientists? Well, here's one of my favorite examples.
Oh yeah. I'm about to drop some particle physics in the club. The LHC is super duper fly. You know what I'm saying. Check it.
27.
So this is the LHC rap, right? Stephen Hawking voice does a rap about particle physics. Amazing, hilarious, very clever, very well done. 8 million views. Oh my gosh, wow. Maybe these folks have cracked like how to communicate particle physics to the public, right? Maybe it's through this kind of rap. Well, they went on and did another example. Black hole rap, 75,000 views. So like you gotta be careful judging the quality of your science communication by the number of views it gets. I mean, there's this example which is one of my favorites. This video, literally just a cat on a Roomba. This thing has 12 million views, right? So you have to be very careful judging your success. And then again, there are scientists out there talking to the public, and I don't know what their agenda is, convincing the public that we're scamming them or we're lying to them or whatever. I don't know what's wrong with Sabina. Of course, there are lots of great examples. Carl Sagan, top notch, recent young people like Katie Mack doing excellent work out there. My journey in science communication actually started with this cartoon. This is a cartoon about the development of the Chrome browser. And like, you guys are machine learning people, you're CS, right? I'm not that excited about browser development. I don't know if you are, but this cartoon was excellent. It got me into the story. I mean, it's Scott McCloud, so it's already very good, but it was a way to explain something very technical, very complex in an accessible way for people who didn't even think they were interested in the topic. So I thought, well, maybe I should use cartoons to explain particle physics. But I didn't have any artistic skill myself. I couldn't draw these kind of things. So my wife, who's also an academic, she's like, ooh, why don't you email Jorge Cham? He's a cartoonist. He knows some science. And I thought, well, you can't just like email celebrities, right? And you email Brad Pitt and say, hey, let's do a movie, right? But I emailed Jorge and he actually wrote right back to me, which is exciting. And it turns out he lives like an hour from me. So we drove down to Irvine and we sat around a table and talked about the Higgs boson for a while, which was a lot of fun. And we put out a cartoon and a video about the Higgs boson. And then this is just before the Higgs was discovered. And so when it was discovered, it was there and it got picked up by all sorts of outlets, New York Times, et cetera. Maybe my favorite moment was when the Higgs boson Nobel Prize was announced. They didn't give it to us experimentalists who discovered it. They gave it to the theorists who thought of it. But in the for further reading section, they list some things you can read about to learn more about the Higgs boson, and they link to our video. And I thought, wow, well, I haven't won the Nobel Prize, but I've been cited by the Nobel Committee. That's like almost as good, right? I don't know. It was a fun moment. So that was a lot of fun. And there was another important moment in the history, which is this book, What If, by Randall Munroe. He's the excellent cartoonist behind XKCD. And this book just went crazy and sold millions of copies. And so his agent reached out to me and Jorge and said, hey, could you guys write a book about science using cartoons? You guys seem to be in that space. And I thought, do I have a book I'd like to write? And I thought I did, because I've realized there's something that's missing in the science communication world, which is that most science is telling us about what we already know. And it makes you feel like, gosh, the universe is mostly figured out. We know what the atoms are made of and what's inside the proton, et cetera. And when I was a kid, I was excited about science because of what we didn't know. The possibility to explore the universe and discover new things. But as you grow up, you realize there's no more continents to discover, right? We have all this amazing technology. You can download every bit of human knowledge into your pocket. You can fly across the world to give a talk. Even fast food companies are creating crazy innovations. And so we decided to write a book about all the things that are not yet understood, the things that can still be discovered, all the things I talked to you about earlier in my talk. So that was my first book, We Have No Idea, I wrote with Jorge. It was a lot of fun, and our approach was not to write an impressive book that makes you feel like you're in the presence of a genius, like Stephen Hawking or Sean Carroll kind of style. Ours is more lighthearted, like let's put in a bunch of jokes and make people feel at home and feel like, hey, if there's dad jokes in here and silly cartoons, then of course I can understand this. And so, we have silly comments about antimatter and anti-books and all sorts of stuff. And the book was a success. It was a lot of fun. It got translated into lots of languages. I feel very sorry for everybody who had to translate my dad jokes into all these other languages. I'm amazed they were able to do that. And then, of course, once you put something out in the public, everybody's tempted to make the classic mistake of reading the Amazon reviews, right? You shouldn't do it, but you're going to do it. So, of course, I did it. So here's the first one I saw. 5 stars. This guy loves the book. He learned, he laughed, he compares it to The Far Side. This is why we wrote the book. Oh my gosh, what a wonderful high, right? Okay, what's the next review? 2 stars. 2 stars. Did we make a mistake? No, it turns out our book about everything that's not understood in the universe, this guy has a theory of quantum gravity that explains everything. And why didn't we talk about his theory? 2 stars. Sorry, dude, we didn't read your paper. Here's a guy who liked it, but please dial back the dad jokes. I don't even know how to do that. That's just how I write. Here's our first 1-star review. Let me tell you, as an author, a 1-star review, that hurts, man. That cuts, okay? This guy, why did he give us a 1-star? Oh, because the book was delivered in the rain, right? 1 star on the algorithm for the rain. So we had a lot of fun with the book, and we went around the country talking about it. And everywhere I went, I met my colleagues in particle physics, and they always asked me the same question. Are you still doing research, Daniel? Cool book. Can you still do research? And yes, these are all the papers I put out that same year that the book came out. Lots and lots of papers, still lots of activity. And in New York, we met somebody who saw us talk and thought, you guys have a fun energy. Have you thought about doing a podcast? And this was before everybody had a podcast, like a year before that. And so we put out a podcast called Daniel and Jorge Explain the Universe. It's just us talking about, antimatter and physics and all sorts of stuff. That wrapped up last year. I have a new podcast Daniel and Kelly's Extraordinary Universe with Kelly Wiener-Smith. She's one of the authors of A City on Mars, an excellent book with her husband, Zach, who's the author of SMBC Comics. And on the podcast, we tell people, hey, you got a question? Write to us. We want to be accessible. I will answer everybody's email. And I get a lot of emails and a lot of questions. And I answer every single one of them, usually within 24 to 48 hours. Even questions like this one. How do you make a bomb to destroy Mars? I debated with my mom. And so I actually wrote to this kid's mom and asked, like, are you raising a supervillain? Should I answer this question? And she's like, yeah, go ahead. I got it. So anyway, I told them how to destroy Mars. And the podcast did very well. In the US, it was ranked number 3 in natural sciences, which is exciting until you see that number 2 is COVID misinformation. And number 1 is Bigfoot. Like, really, people? This is natural science? In the UK, they're doing something right. I don't know if they don't have no Bigfoot in the UK or what, but we were number 1 in the UK, which is exciting. Get lots of feedback on the podcast. Here's a lady who always loved physics, and because of the podcast, went back to school and got her degree in astronomy at 60. Like, that's inspiring. That's why I do this. People out there who love this stuff, their lives went a different direction. This encourages them to come back. Here's somebody who's like says, Dr. Whiteson podcast legit got me through 2020. Like, that's nice to hear, right? Here's somebody who loves the podcast because my voice puts them to sleep, right? And that's cool. Like, as long as you download it, I don't really care what you do with the podcast. Here's a guy who loves the podcast because it drives his wife crazy on long drives. Like, I don't want to be in the middle of anybody else's marriage, but apparently I am. So we got lots of questions in the podcast. We wrote another book called Frequently Asked Questions about the universe. A lot of fun. All those questions that we get about the podcast. And my recent book came out last year is this book called Do Aliens Speak Physics with my friend Andy Warner, another nonfiction cartoonist. And this explores what might happen when aliens arrive. I mean, maybe they'll zap us from space, maybe they'll eat us, or maybe, and this is the scientist dream, we'll get to talk to them about physics. If there's some super advanced race because they've gotten here, maybe they know, how to build a warp drive or teleport through space or figure out quantum gravity. Wouldn't that be incredible, right? And lots of scientists like Carl Sagan think that it's obvious that we will have physics in common with aliens, that when they come, they will be working on the same project that we are working on. That the way we describe physics is inevitable and unique, and therefore alien minds must also build the same structures. That 10 minutes after they get here, we'll be at the chalkboard talking about quantum field theory Lagrangians. So this book argues that maybe that isn't true. Maybe when aliens come, their way of thinking and talking about the universe will be more alien than we can even imagine. Science, for example, is a cultural thing that we do. Is it clear that aliens will even do science? Do you have to be curious about the universe in order to develop technology? How do we know that we can use math to communicate with aliens? We have human philosophers who think that you might not even need math. Here's Hartree Field, who wrote a whole book called Science Without Numbers, where he developed a theory of gravity that doesn't use any numbers. It's crazy, people. So the book also explores, would aliens ask the same questions? Would their answers be intelligible to us? So it's a fun book. It's the same sort of lighthearted style, but it touches on deep philosophy questions. Last thing I want to tell you about in the last few minutes is about a TV show I worked on. PBS put out this call for a TV show, and so we wrote a new show about little animals that ask questions, and they don't know the answers to their questions. They have to go figure it out, and the adults on the show don't know the answers. So the adults aren't afraid to say, I don't know, let's use science to figure it out. So we pitched this idea to PBS, and you know what happens when you write a grant proposal? You pitch it, you expect to never hear back. PBS called us up, and they're like, we like your idea, make us an episode. And I thought, what? How do you do that? So I literally typed into Google, how to make TV show. And so I learned, and we worked with animation studios, and I learned special software for writing scripts. And the show came out, and it was well received. It was a lot of fun. Lots of people really enjoyed the show. It's got a catchy theme song. It encourages kids to ask questions. It also encourages parents and teachers to say, I don't know, let's figure it out, which I think is a big barrier for people to talk to their kids about science. So I've done a lot of science communication, and sometimes I get questions like, are you still doing research? Does this hurt your career? If you're a young person, should you get into science communication? So I post these questions to Sean Carroll and Stephen Strogatz, two guys who are also doing science communication and yet are very successful researchers. And both of them say, like, basically, don't do science communication until you get tenure because it's dangerous for your career.
You're going to do it.
I'm still doing research. I want to assure you my productivity has not dropped from doing science communication. And I want to share you very quickly a personal story, which is when I went up for promotion at UC Irvine to full professor just in this period, the department voted on my case, and I got 21 yeses and 7 nos. And in the sunshine of Southern California, this set a record for the number of no votes on a case. Like, it's a very congenial department. So there are a bunch of people in my department who wrote comments like, why is he spending all this time on books? Like, less science communication, more science. Got all these nasty comments on my case. The good news is, when the case went up the ladder through the campus, the provost at the university saw it, and he'd actually read my book, and he thought, this is ridiculous. And he wrote a specific comment. I'd never seen this before. The provost get involved and write a comment on somebody's case. And he says, actually, this is important work and we should support it. And he gave me an extra promotion on top of it to send a message back to those guys in the department to say, actually, this is important that we should support it. So things are changing. All right, so why do science communication? I think it's important. There are people out there spreading nonsense, like these guys on Twitter, who don't understand the Big Bang, and so they think that pretty much everything you've been taught about how the world works is a lie, right? Which it isn't, obviously, but if you don't understand science and you can't represent it correctly, it might seem that way. Here's one last story to share with you. I got an email from a student, a 12-year-old in 2019. She'd been listening to the podcast, she was really interested in it, she had questions, she asked my advice, I wrote back to her. Last year, she wrote to me again saying, hey, it's me. Now I'm going to college, and actually I'm coming to UCI to do a physics major to study with you. And then I got to meet her. I was like, wow, this is an actual person I've met who I've influenced in their life. And so that's why I do science communication. Thank you very much.
Thanks, Daniel, for the amazing, inspiring talk. We have a time for maybe a question or two, so please feel free to call out. Yeah.
Thanks for your talk. This is Rosina Weber from Drexel University. I'm really fascinated with your work, particularly how you're bringing into this, the relevance and the importance of interdisciplinarity to this conference that sees and wants to open up and see the diverse influence of AI. But the topic you're bringing up is of extreme importance, how we're not motivated and incentivized to do science communication, and how the lack of it is bringing us to the verge of maybe the end of science funding. And from your experience and your brilliance on this, tell us, what can we do individually and as groups of people to make it better and prevent this bad risk we're facing?
It's a really important question you're asking. And you know, folks like me, we have a small platform. It's much easier to get a huge platform if you're a grifter. If you want to sell the story that scientists are lying to you and they have secret wormhole technology that the government is keeping secret because they got from the aliens, you can get a huge platform. There are people like that. That is not even an exaggeration. Like, people like that have massive platforms. It's a much easier story to sell. So I wish I knew how to solve that problem. All I can do is try to tell the truth and try to communicate and try to be accessible to folks out there who are willing to engage in good faith. But we are drowning in folks engaging in bad faith and lying to people and manipulating them. And yeah, I wish I knew how to solve that problem, but I agree with you. It's a really, really important problem. And it's why we're seeing a lack of support for funding for science and a lack of funding for science. So it's potentially civilization destroying. I totally agree. I wish I could solve it.
So, Daniel, thanks for the great talk. Let's thank Daniel again. And what I'll say is that this hopefully will start the conversation. We can take questions offline. Thank you so much.